In this video, we'll learn how to use Excel to find a quadratic trend line, that is a second-degree polynomial, for the best fit model. We've been given some input-output data. This is the original data set. I've already created the input-output graph, scatter plot for that original data. In order to create the trend line in Excel that will best fit this data, I click on one of these data points, it doesn't matter which, and then I right-click and select Add Trend Line. I now need to select the type of function that I want to use for the best fit trend line. I said that in this video we're interested in finding a quadratic model. Now that makes sense because you see that the scatter plot sort of has the shape of a parabola, an open up parabola. So a quadratic function does seem to make sense. Remember, a quadratic function, a parabola, is a polynomial of order 2, polynomial of degree 2. So I select the polynomial and make sure it's set to order 2. Don't forget to also select display equation on chart. So here is my quadratic, my second degree polynomials equation. Next, I click on the text box that contains that quadratic equation. I right-click and select Format Trendline Label. You then need to select number and tell it how many decimal places that you want to round the coefficients. For this particular video, I'm going to go ahead and round my coefficients out 4 places. All right, now I have my equation. There is the trend line, the quadratic trend line, the best fit quadratic function for this data set. All right, now I'm going to go ahead and take that quadratic function and I'm going to create a new input-output table and graph using the quadratic model. So I have a new input-output table. This time I'm going to have x values, and I'm going to label the y values as the predicted y values using this quadratic model. We expect that the y values we get will be similar to the y values from the original data set, but since it is only a prediction model, it's not going to be perfect. The y values will be slightly different than those found in the original data. I'm going to go ahead and copy the original x values. And then I'm going to write an equation using the trend line equation in order to predict the y values. So I wrote an equation here that takes 1.0136 times the x value squared minus 35.65 times the x value plus 339.9091. Press enter. I drag that formula down to all the rest of the y values. And now you can see when x is 0, the original data value was actually y equals 330. The model predicts a y value of 339. As another example, when x is 40, the original data value was 500, and in our model, when you plug in 40, you get 535. So it's a little bit different, and that's how it's always going to be. I can now take my input-output table using our prediction trend line, our quadratic trend line model, and I can create a smooth line graph. There it is. Looks like a quadratic function, which makes sense because it's a quadratic equation, a quadratic model. I could then also use this quadratic equation to make predictions for other x values. For example, if I wanted to predict the y value when x is 38.7, I could plug in an x value in the table of x equals 38.7, press enter, and it would tell me that we predict a y value of 478.312. I could also use Solver now. If I wanted to know when this model predicts a y value of 400, I see that it seems to hit a height of 400 here. That happens somewhere around 35. So I could put my cursor in that y value cell and use Solver by putting the y value cell in the objective, a value of 400, and the x value cell in the by changing variables. Hit solve, and it tells me that at about 36.7834, the y value is predicted to be 400.